Hello friends, my name is Sushant and I'll be giving a demo on the hardware accelerator for 128 FFR filter, which is our final project for the WE278 class. So we'll be evaluating first the performance of the software implementation of the 128 filter written in C code on a NEOS processor with the hardware implementation of the same made as a custom component with the help of the QSys designer, which will be prototyped on the FPGA board. So we'll start first by building a new Quartus project for the hardware, for the software implementation of our QSys. So we will set the working directory. We will give the name as FIR QSys software. Then we need to select the proper FPGA device cyclone to the pin count as 484 and proper FPGA device. We need to do settings of the simulation too. So after this we need to start the QSys. So this is the QSys designer. So we need to instantiate a NEOS processor in it. We will select the NEOS 2 economical version. After that we need to select an on-chip memory. We will select the number of memories, number of bytes as 8192 in order to overcome the problems of buffer overflows. Then we select the standard JTAG UART interface for us. And in the end we need to select the performance counter. So as all of the components are in place, we need to make the connections in the QSys. So make the global clock connections first to all of the components, and then the global reset connections with the between the master and the slave components. Then the data master from the NEOS to processor will go to each of the slaves here: on-chip memory, data queue, and performance counter. But the instruction master will only go to the on-chip memory. Then we need to assign the base address for all of them. We need to assign the interrupt controller, and in the end we need to configure the new. So we now need to make the reset vector memory of the NEOS processor to on-chip memory, and also the exception vector memory of the NEOS processor to the on-chip memory. Then we should click finish, and as most of the parts is done, there is no errors over here. Then we should save the system, and while saving the system we need to give the same name as the top level hierarchy of the project. So after the generation of the QSys system, QIP file will be generated, which we need to incorporate in our Quartus project, and we should start the assignment editor for assigning the proper pin values. So both the pin values will be clock underscore clock location. The value will be pin underscore L1. As you can see, we have made proper assignments over here. Then after saving the system, we need to start the compilation. The compilation will take a while to happen. As you can see, the full compilation is successful. After this, it will generate a SOF file which we need to dump on our FPGA board. Starting the programmer, we need to search for the SOF file, and we need to program our FPGA board with this SO file. So the programming is successful. We need to save this CDF file and then we can close this program. We need to see the needs. We can NEOS 2 application BSP template and we need to do the proper settings. As you can see, the NEOS 2 BSP template has been created. We need to first run the small hello world program to see if the proper communication has been established between our FPGA board and the NEOS system. So we need to just build the project first. So now we will run our FIR filter code onto the NEOS 2 hardware. Now build the code again and we run on the NEOS 2 hardware to test the implementation of a FIR filter on the FPGA board. It's finished. And yeah, so as you see, we got the filter output to be -34, which is the expected output, and the compression completed in 1.7489 clock cycles. And we will now run the hardware implementation of the FIR filter and compute the clock cycles obtained there. With regard to the clock cycles obtained in the software implementation, which is 1.75489, and thus we can make a comparison between the hardware implementation and the software implementation of the FIR filter on the NEOS. Thank you guys, and we'll proceed now with the hardware implementation. Thank you. So the hardware implementation of the rest of the parts are exactly the same. Only difference is creation of a new custom component for the FIR filter. So we open the QSys and we try to create a new component. We'll give the name of the component as filter FIR 128 tab, and the same name over here to avoid confusion. Group may be custom component. And we add the Verilog parser here. Set the top file as the top level file, where we have the interface. So we associate the clock and the reset buffer in the interfaces. In designing the QC system, the rest of the part is same as the software implementation except for addition of this new custom component over here in the system. We add this and we make the connections as we did for the software implementation. So we have added a QIP file. After the adding of the QIP file, we begin the compilation process, and then we will download the generated.so file onto the FPGA board. So the full compilation was successful, and then we open the programmer to download the .so file onto this. Start the program. So it's successfully programmed. So the part is successfully dumped onto the FPGA chip on the FPGA board. So we should get a header from NEOS 2 after building the C code here. So now we will build a project and run as NEOS 2 hardware, and we hope to get the header from NEOS 2 as well for the hardware implementation.
No, what he's asking is how will it understand what to do?
Oh yeah, so as you can see, we got the header from the NEOS 2. Now we will implement the FIR filter code and hope to get the same value, which is -34, as we get in the software implementation. So this is the FIR code for the hardware implementation part, and we'll run and see what result we'll get. So run as NEOS 2 hardware.
So the first one has to be this one, random number generator.
And okay, so it's yeah, see. So We have successfully got the result. The result here is minus 34, and the computation completed in 21623 cycles. Um, so now we can evaluate that with respect to the software implementation and see the performance uh, measurement of like which is better, the hardware implementation of the Neos is better or the software implementation is better. So the result is matching, so the project is successful. Thank you guys, and thanks for listening my video. Thank you.